Good day, everyone. I'm Chandler, and my co-author is Dr. Randy Cahote from University of the Philippines, Diliman. And today I will be talking about our research in improving the detection of small-oriented objects in aerial images. Object detection has been used in many applications of computer vision. However, these detection methods use a horizontal bounding box that does not model the orientation of oriented objects. For the case of objects in aerial images, using this kind of bounding box cannot accurately enclose oriented objects. Therefore, we need to design an oriented bounding box for arbitrary oriented objects. Previous methods that use OBB vary in different methods. Despite very effective in detecting oriented objects, more attention is needed to detect oriented objects that are small in size. So, we present the details of our proposed small oriented object detector with attention points network with two new loss functions, guided attention loss and box points loss. The attention points network uses the ROI and refine them in the self-attention using GA loss. Then the attention features are used to represent box points and regresses them to the OBB using the BP loss. To make sure that we highlight the object in every ROI, we use a loss function that compares the attention features and object mass. The input ROI is transformed into three vectors, queries, keys, and values, then processed by self-attention to obtain attention features, which are compared to object mass using guided attention loss. These mass are obtained by converting the bounding box into instant segmentation of the object. The computation of the GA loss given the algorithm above. GA loss compares the per pixel similarity of self-attention with ROI features and the mask features using cross-entropy function. The BP loss is a function where we calculate the distance between the target OBB and box point located at ij as shown in the figure. When the box point is connected to all the vertices of the OBB, it forms four separate triangles. These triangles are used to identify if the box point is inside or outside the oriented bounding box. Now we compute the relative position of a box point either inside or outside the bounding box, as shown in the equation in the right. However, this equation is non-differentiable, so we design a kernel function that can approximate the BP loss. The parameter we use to compare the performance of different methods is the mean average precision. MEP is the average precision of each class averaged over the total number of classes. Now, to evaluate our method, we use two datasets, DOTA version 1.5 and HRAC 2016. Our method has a marginal increase of MEP 50 over the baseline at rainfall test split, but obtain a large improvement of 7.5% when using the train test split, as shown in the table. Now in table 2, we showed that our method achieved a very high performance increase versus the baseline across MEP 75 and MEP 50 to 95 evaluation metrics. For HRSC 2016 dataset, our method obtained the highest performance. Now for visualization, the figure 4 shows sample detection results on DOTA version 1.5 and figure 5 shows sample detection results on HRSC 2016. To evaluate the effectiveness of each loss functions, we also conducted ablation experiment. And to show that our loss functions learned during training, we plotted the learning curves. In conclusion, results show that our method was able to achieve better results against the baseline and other architectures on the two datasets. Lastly, we would like to thank everyone who helped us in finishing and funding this research.